Hello, today we're going to be talking about terminating decimals, and when we teach our kids about terminating decimals, we want them to really understand the place value and what theorems we can use to help us discover when we're going to know a number terminates. So a terminating decimal is a decimal that can be written with a finite number to the right of the decimal place. And not every rational number is going to terminate. And so we can use theorem 7.1 to help us understand when a decimal is going to terminate and when it's not. And theorem 7.1 says a rational number, a over b, in simplest form can be written as a terminating decimal if and only if the prime factorization of the denominator contains no primes other than 2 or 5. So we know that in our number system, we use base 10. And so here's the decimal place, and these are all our whole numbers that we have over here, ones, tens, hundreds, but we have the decimal place and we go into tens, hundreds, thousands, 10,000s, and so on. And so really all this is representing is 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000, and we just keep adding zeros as we move further away from this decimal spot. And so theorem 7.1 says that if we can use 10, because 10 is our base number that we work with in our number system, if we use 10 and we do the prime factorization of 10, well, what factors go into 10? Well, we know 2 goes into 10, and how many times does 2 go into 10? 5 times. Well, we can't break any of these numbers down anymore, and so these two are both prime numbers, and we know that because of this theorem, this decimal is going to terminate. So let's do a few examples of how we can test this theorem using theorem 7.1, okay? So like I said, let's start with 1/30th. Like theorem 7.1 said, we just have to do the prime factorization of the denominator. So let's take 30 over here and do the prime factorization. Okay. Well, 6 and 5 go into 30, and 5's a prime, so this doesn't go out any further, but 2 and 3 go into 6. Well, here's 2 and here's 5, like theorem 7.1 said, but because we have another prime 3, this fraction will not terminate because the 3 is in this prime factorization. Now let's take 3/30ths and try this. Again, we're just going to take the 30 because that's the denominator and do the prime factorization of it. Let's do it a different way. Let's say 3 and 10 are both factors or multiples of 30. And so then 3 is a prime, so it cannot go out any further. But 10, we know, separates into 2 and 5. Now this is a different situation. We have the 2 and the 5, so that's okay, but we still have this 3. But because there's a 3 on the top of the fraction, the 2 3's cancel, and we're just left with the 2 and the 5, and so therefore 3/30ths will terminate. So as we get this understanding down with our students, we can even complex this idea a little more, and we can take an example like 3 over 2 squared times 5 cubed. All right, well, we're looking at this, and based on theorem 7.1, we want to have tens in the denominator. And we're looking here, and there's 2 2's, and there's 3 5's. So we have 1 pair of 10, 2 pairs of 10, but this 5 isn't a pair. And for this to terminate, we have to have 10 pairs. So we're going to add a 2 to this problem to make a third 10 pair, okay? So then we add a 2, and we're just going to multiply this whole problem by a 2. This allows this to now be 2 cubed times 5 cubed, which equals, we know that 10 cubed is 1,000, and 3 times 2 is 6. So 6 thousandths, we know that because of our place value that we talked about earlier, we're just going to put the 6. The 6 is going to be in a thousands place. So decimal, tenths, hundredths, thousands. So that's how we can complex this idea of terminating decimals, and how can we get this kind of problem to terminate. So today we learned about Theorem 7.1 and how we can teach our students when and when not decimal is going to terminate based on the prime factorization of the denominator.